All right, section 3.1 is about shortcuts to differentiation. So what we're saying here is that we could prove all this with the limit definitions of derivatives, but we don't have to do that every time, because once we do that enough, we will see the same patterns in that limit definition. So now we can go ahead and use these more efficient methods. So our first shortcut, or what we might call a derivative rule from now on, is we're going to see graphically. So I have this graph right here of f of x, and I want us to look at the tangent at a certain point. Just for an example, let's look at the derivative at the point 2. So below it, what I have graphed is 3 times the function f of x. And again, just visually look at the tangent at that same point 2. What we should see is that it's clearly steeper, and hopefully we are going to guess that it is 3 times steeper because we have multiplied the function by 3. On the next graph, I've actually done 2 things. What I have graphed is negative f of x over 2, or you could also see that as negative 1/2 of f of x. And here we should see both of those transformations per se. If we look at the tangent at 2, first of all, we can see now that the tangent has indeed changed signs. There used to be a decreasing tangent, now it's an increasing tangent, again because of the negative. And what we should also see is that it is only 1/2 as steep as the original tangent up here at f of x. Below here, I just have all 3 of them being compared. So if we look at this one as our kind of starting function, we can multiply it by 3 and get a steeper derivative, but it's still just 3 times the original. And then same thing here, we could flip it with a negative and decrease the steepness by 1/2. So in other words, if we have a constant multiplier in front of a function, we can pull that constant out and it becomes a multiplier in front of the derivative. So for example, we looked at the derivative of f of x at a point. Let's just say for easiness it was equal to negative 2. And then on the last page before this, we multiplied that function by 3. And what we did notice was that the derivative was just 3 times greater than at that point. Just as a quick little proof as to why that works, we're going to go back to our limit definition of the derivative just to enforce again that all these rules can be proven using our limit definition. So we're looking for the derivative of a constant times a function. So we introduce our limit definition. Then from there, we're going to rewrite the multiplication on the numerator. So I'm just going to pull that c out in front of the function. So again, I just took this c right here, which is being multiplied, and move that multiplication in front of that fraction. The reason I did that there was so now we can apply some properties of limits, which means we can pull that constant out of the limit. And then even further, just by definition, then we pull that constant out. So our constant is in front of our function. And by definition of the limit definition of the derivative, this is our derivative. So our next theorem is going to involve sums and differences of functions. So I've just defined 2 functions, f of x and g of x, just kind of arbitrarily. You don't necessarily need to know the formula at all, but let's just look at the rate of changes, and then let's look at what happens when we add those functions together. So for instance, we'll fill in this column over here. This would be 100. If we add these together, this would be 100.1, because again, we're just adding f and g of x. So 130.2. 160.3, and this would be 200.4. Well, let's take a look at the change in f. Here we can see that it was increasing by 10. Here we can see it went up by 20. Here we can see it went up by 30. And here we can see it went up by 40. Let's look at the change of g, just kind of arbitrarily right now as its own. So here we can see it increased by 1/10. And it's a constant increase of 1/10 for the entire time. Now the pattern that we want you to see for our rule here is that the change of the sum of the function happened to be 10.1. So where did that change come from? Well, obviously we got 10 from the change in f of x, and then we got 1/10 from the change of g of x. So if we added those 2 differences together, look at that, that's the same difference between the sum of our functions, and we see that will always happen. So at the next change, we saw g increase by 20, and we still see that g of x increases by 1/10. But if we look at the summing function and ask ourselves, what did that change by? Well, I would assume 20.1, because 20 plus 0.1, and again, we do see that in our summing function. this change here was 20.1. The change between these two was 30.1, which again comes from 30 from the change of f of x, and then another 10th from the change, of g of x. So we'll move to our general formula, and you just need to fix a typo in your notes here. This should say if f and g are differentiable functions, then what we can say is if we were looking for the derivative of two functions added together, or in other words, the derivative of the sum of two functions with respect to a common input x, what we could just do is find the derivatives independently and add them together. This rule will also apply to subtraction by the same proof. So for our quick little proof, we will go back to the limit definition of the derivative. So if we wanted to prove that the derivative of the sum of two functions would be the sum of the two derivatives, we'd start like this. And it will obviously apply the same to the difference of two functions, which I'll leave that proof to you. So first of all, we're just going to apply the limit definition of the derivative. So I've inputted x plus h in the correct places, so on and so forth. Now the next thing that I've done is I've just rearranged the terms a little bit. So let's go back and look at how I wrote it originally. So like here, f of x plus h was positive, and down here I just kept that positive. But this negative would have applied to the f of x. So instead of writing it back there, I've just chosen to write it there. And the original original limit definition has a divisor of h. So I've just given everything, again, that divisor of h. Similar with the g of x plus h and the g of x, here g of x plus h was positive. So I've just put that over here and obviously kept it positive. And then this negative right here also would have applied to the positive g of x, making it negative. So I've just wrote that back here and again given it the denominator of h. Now we've obviously rewritten it for a reason, and the reason we've done that, and I'm also just going to imply the addition property of limits at the same time. But what I've highlighted in yellow, that is the definition of the derivative of f of x. And what I've highlighted in blue, that is the definition of the derivative of g of x. So by that limit property, or the addition property of limits, we can just conclude that this will be true. Now the next shortcut in the textbook is the power rule for a derivative, which we've already looked at once. I just want to take a moment to make a few comments on this rule here. So first of all, it's really important to differentiate between the types of functions that we can apply the power rule to. The power rule only works if our variable is the base of the exponent. So for instance, something like this, x to the third, we could apply the power rule here because our variable is the base of the exponent. But something like this, 2 to the x, this is not something we can apply the power rule to. The power rule, again, says x has to be our base and not our exponent. So please understand the limitations of the power rule. The power rule will apply to any type of exponent, though. So we have quick 3 examples just to help you out with that. So like here, 1 over x to the third, that's x to the negative third. So we can apply the power rule to this because our variable is the base of the exponent. So we'll drop that down. -3, the x is obviously still there as the base here, and then we'd have to take our original exponent and decrease it by 1, which would give us a -4. Fractional exponents work just the same. The square root of x can be rewritten as x to the 1/2 power. So that 1/2 would slide over in front and be our coefficient. X will stay the same. And then we'd have to decrease our original exponent by 1. So 1/2 minus 1 now becomes -1/2. And we'd rewrite that like this. And more commonly, we would put it back into the square root. So if this was f of x, this would be its derivative. Lastly, just more complicated fractional exponents. So here, 1 over the cubed root of x. So the cubed root of x is just x to the -1/3. So that becomes our multiplier, so 1/3, and I'd have to decrease the original exponent by 1, so negative 1/3 minus 1 becomes negative 4/3. I'm just going to go ahead and take that negative exponent and move it to the bottom of the fraction. And what would probably be common is to put it back in that radical notation. We have 3x is our radicand. It's going to be the cubed root of 4. I think it is important to see again kind of the limit definition proof of this, because we've already seen a geometric proof with area. So before we jump into that proof, though, just a quick little background. I'm just asking you to look at a pattern here. This is the binomial theorem, essentially. We're just looking at the coefficients when we expand a binomial. So if we have like x plus h, that's our binomial. We're going to raise it to some power. So like here, x plus h would be x squared plus 2xh plus h squared. We all know that one. Just a few more examples that I have prepared so we can see the pattern. We're looking at the pattern and the coefficients of our variables. So like we can see things like if I raise it to the 4th power, then the first term has that 4th power. But the next term will be 4x cubed h. And then we'll see like here kind of the power, well, this kind of decreased by 1 and the h kind of increased by 1. It used to be 1, now that's a 2. If we kind of look down here at this binomial to the 5th power, again, we can see some things like the biggest term has that biggest degree of 5, but this term has x to the 4th power and then h to the 1st power. But the next term has x to the 3rd power and h to the 2nd power. And then the next term, the exponent on x decreases by 1 and h increases by 1, so on and so forth. So in general, we see that pattern. And we can see a pattern in the exponents on x and the exponents on h. And that's primarily what I'm asking you to look at right now. Now that pattern will go all the way. So in other words, what we're saying here is that they start with like 5, and then the x will go to 4, like it did up here, and then 3, and then 2, and then 1. And eventually it's going to go on until x is to the 0 power, which would just be 1, right? Which means we just have h to that power of n, just like we do up here. Like this was a binomial to the 5th power. So we see x to the 5th, the 4th, the 3rd, the 2nd, the 1st, and then here it's technically x to the 0th power. And we see that backwards with the h's. Right here, technically, is h to the 0 power. And then we can obviously see h to the 1st, h to the 2nd, h to the 3rd, h to the 4th, h to the 5th. So using that little shortcut, we're going to apply the limit definition of derivative. So if we're trying to find the derivative of our power function, apply our limit definition. So I plug in x plus h. So we have x plus h to the n minus x to the n. Now I'm going to expand that binomial, x plus h to the n. And I'm, again, just simply using the pattern that we looked at on the last slide, and I've copied here. So I've just reintroduced that pattern, and then obviously minus x to the power of n. So we're going to do a little rearranging. What we can obviously see is like x to the n and negative x to the n would obviously undo each other. So like something like that would go away, and something like that would go away. But what I'm also going to do then is that all the terms that I've left after I've canceled out those x to the n's, every term that I've left, like this one here, and then all the ones in the middle, they all have an h in it. So I'm just going to go ahead and factor out that h at the same time. Now what we're looking at here, after we cancel out those h's, is that one term left after we cancel out that h will not have an h left in it, right? Because this original term that was left here, after we canceled out x to the n, this had h to the power of 1. So here, after we factor out h to the power of 1, that first term doesn't have an h in it. But every other term will, right? The term in the middle had h to the 2nd, h to the 3rd, h to the 4th, h to the 5th, h to the, so on and so forth, until h to the n. So all the terms that are left, all of them that are left, will have a multiple of h. And if h is going to 0, all those things will also go to 0, so we are simply just left with that one term that doesn't have an h in it anymore. So we have proved the power rule. So at this point in the notes, we have finished the content for today. So just summarizing what you need to be responsible for is just these three, technically four new rules of finding derivatives. So we have our constant rule here, we have our sum and difference rules, and then we also have our power rule. So you need to be able to know when to apply them and how to apply them. If you want to see a few quick practice examples so you can see them in action, you're going to continue the video. If you feel like that's all you needed to see and you're ready to jump on your own, well then you're ready to go do some work. So here we're supposed to find the derivative of f of x using the sum and difference rules. So what we can kind of say here is that we have a function, f of x, that's being defined by three separate functions all being added together. So we can extend the sum and difference rule and say we could just find the derivative separately and add them all together. So first we'd find the derivative in respects to x of 5x squared. Then we would add the derivative of 3x with respects to x. And then we would add the derivative with respects to x of 2. Now, the first one here, we can just apply the power rule. So we'll slide down the 2. So 2 times 5 is 10. And then decrease the exponent by 1. So we get 10x plus, again, we'll use our power rule. This is 3x to the first. So we slide that 1, becomes a multiplier of 3. And then we all know if we decreased 1 by 1, that'd give us x to the 0 power. And x to the 0 is just 1. So I'm not going to multiply by 1. And then lastly, with respects to x, what's the change of 2 going to be? Well, that's just nothing. If I change x, 2 is always going to be 2. There will be no change there, so the derivative is going to be 0. So in other words, the derivative of our original function will follow the function rule of 10x plus 3. The next one is just another example just showing that it's just not as nice. So what we could do is we could find all the derivatives separately and then add them all together. So this first function, if we found the derivative with respects to x of that, we would then add the derivative with respect to the same input of that function, which just has a weird number as a radical, or excuse me, as an exponent, and then we would add the derivative here. And I am going to take a moment to go ahead and represent that as 1/2 times x to the negative 1/2, just so I can start to set up some more rules moving forward. So here, the first one, we will just simply apply the power rule. So if I multiply the 3, I get 0.3x, and I got to decrease the original exponent by 1. Moving on to our next, I'm just going to go ahead and pull out the multiplier, right? We're going to use the constant rule. So this will just be 2 times whatever the derivative is. So I'm going to add 2 times whatever the derivative without the multiplier of 2 would be. Now here, again, we're just going to apply the power rule. So the exponent becomes a multiplier. Base stays the same. And then I'm going to write it as root 2 minus 1. And at this point in the game, I don't really want to simplify that, and I wouldn't expect you to either. I know that it's still going to be positive, though, so I'm going to leave x in the numerator. In other words, not turn it into a fraction, because the square root of 2 is a little bit bigger than 1. Same thing with our last term here. I'm going to go ahead and pull out that multiplier, and whatever the derivative is of what was left over. So in other words, the derivative of this, which we kind of went through before in one of the examples in the notes, but we'll still do it here. So we pull down the multiplier, so we have negative 1 over 2. And then if I take the original exponent, which was negative 1/2, and subtract 1, that would give me negative 3/2. So the negative exponent, we'll send it to the denominator. So I'm just going to do that right now. This would be x cubed. So just kind of clearing up all our work, our final answer then. So the derivative of h would be defined by this function here. To find the first and second derivative of our function, we're just going to apply the power and the sum rules. I'm going to do that all at once. So the derivative h prime So that'll drop down as a multiplier, so negative 9.8 t. Then this 1 becomes multiplier plus 5. 1 minus 1 is 0, so t to the first is just 1. I'm not going to mark that multiplier. And we know that the rate of change of the constant won't affect it. So therefore, to find the second derivative, we would just apply the power rule to the first derivative. So t to the first power, that becomes multiplier, negative 9.8. And then 1 minus 1 is 0, and we know that t to the 0 power is just 1. So this is our second derivative. And you should see 9.8 as acceleration due to gravity. Moving on to the next example, first I'm going to simplify this before I try to find the derivative of it. So everything has a common factor of t squared. So I'm just going to pull that out of everything. And cancel it and just kind of rewrite our function in simplified terms first. So we have t squared plus t minus 1 over t to the third. Now from here, we wish we had some sort of like division rule, which we don't know yet and is a little more complicated than you would maybe kind of assume, so we can't use it. So I'm just going to rewrite this function as a sum so I can apply the sum properties that we talked about. So it'd be t squared over t to the third plus t over t to the third minus 1 over t to the third. Then from here, we can use our sum and difference properties. So we're going to find the derivative of this, add it to the derivative of this, and then subtract the derivative of this. Let's go ahead and do that. So here we'll obviously simplify a little bit further. This is just 1 over t, or in other words, t to the negative first. So the derivative of that, we drop that down, so negative 1t, and then going back I'd have to subtract 1 from the original exponent, which would be a negative 2, which I'm going to go ahead and just leave like that for right now until I can kind of figure out how I want to combine all my derivatives. So now we're going to look at the derivative of that middle term right here. So again, we will also simplify this as 1 over t squared, or in other words, t to the negative second. So if we use our power rule, this comes over here, so a minus 2. And if we go back and subtract 1 from the original exponent, t to the negative third. Finally, we'd have to subtract this, which I'm just going to write as t to the negative third. Now that multiplier will come down, become a positive 3. And then when we go back and subtract 1 from the original exponent, negative 3 minus 1 becomes a t to the minus fourth. So finally, everything here, we could leave it like that, I suppose. Everything here does have a negative exponent, so we could obviously simplify those rules of exponents. So our derivative would be negative 1 over t squared minus 2 over t cubed plus 3 over t to the fourth. And I think at this point I'd rather just leave it like that because I think that has a nice little simplistic beauty too. We can see the pattern of 1, 2, 3, and 4. We can see the increasing exponents on top. We don't necessarily need to combine those all with a common denominator. But if you wanted to, it should be there now, and all I did was, of course, find that common denominator of t to the fourth. So like here, I would have multiplied by t squared on the top and bottom. Here, I just would have multiplied by t, and that already has a common denominator. Either one of those answers is good. Whereas the function increasing and concave up. So increasing we will address first. We know increasing is just simply where our first derivative is positive. So we find our first derivative using the power rule and then our difference rule. So we have 5x to the fourth minus 5. So I've just inserted a graph of that derivative function just so we can just graphically see when it would be increasing. Obviously, we do have the skills to do this algebraically. To do a quadratic inequality, we just factor out the 5x to the fourth minus 1, and we'd ask ourselves, when would that first derivative be greater than 0? Right now we could, so what we look at is when is 5x squared minus 1 times x squared minus 1 all greater than 0. So we could kind of work on that. Obviously, we'd have cases where like it would be positive and positive, or we could have a negative and a negative. So we'd set x squared minus 1 greater than 0, so on and so forth. But right now we're just going to look at it graphically. We can see that our derivative is positive when it's above the x-axis. So we would say that it is increasing on the interval from negative infinity to 1, sorry, negative 1. And then again from 1 to infinity. To address when it's concave up, we have to find the second derivative. And it's concave up when our second derivative will be greater than 0. So our second derivative, again, we would just apply that power rule again. So dropping the 4 gives us 20 x to the third. And then that goes away because it doesn't have an x on it. So this is our second derivative. Again, we could graphically think about this one just as some sort of vertical stretch of a cubic function, which we know goes to the point 0, 0, which I'm trying to emphasize, that it goes through 0, 0 here. So we know that any of the x values, this will be a negative value. So when is it positive? Well, it's positive here. So our original function would be concave up on the interval of 0 to infinity. I'm not going to let us move on without actually seeing if that's true on the original function. So this is the original function. We said that it was increasing from negative infinity to negative 1. I'm just showing negative 1's right there. Here's 1, and we said it was increasing from 1 to infinity. And we can clearly see that it is. The second thing we said was that it was concave up on 0 to infinity. And we can obviously see that here too. From 0 to infinity, this graph is concave up, compared to before that, where it is concave down. So we have some function, and we want to find the a value and the n value. They'll make the following properties true. So first we should calculate the derivative of our function. So the derivative of f of x will be a times n to x to the n minus 1. So what we're looking for here is that f prime of 2 is equal to 3, and we also want f prime of 4 equal to 24. So just rewriting, what we're saying is we have the definition of the derivative here. So we know that a times n, I'm just going to put in parentheses. Now our base was 2 here, 2 to the n minus 1. That should equal 3. And then over here, again, what we can say is that our derivative function, which is really a times n, and then here x is 4, so 4 to the n minus 1, that should equal 24. Now what I'm going to do is I'm just going to set up a fact. I know that 24 over 3 is the ratio of these two derivatives. So 24 is the same thing as a n to the 4 to the n minus 1, and then 3 is the same thing as a times n to the 2n minus 1. And I'm just comparing these two values, so now we can obviously do some simplification. So we will cancel that. Now here we'll just apply some properties of exponents. So if the numerator and the denominator have the same exponent, we can just apply that to the entire fraction. So we have 2 to the n minus 1 must equal 8. So therefore we know that n minus 1 must be 3, because 2 to the third is 8. So here we get n is equal to 4. Now we need to find a as well though, so I'm just going to kind of just do that over the top of this. So if n is equal to 4, what we can do is just go plug that back in. I'm just going to go ahead and do it right here. I'm going to plug n back in and then try to find what a would be. So we had a, and we know n is already 4, so that's times 4, and we know 2n minus 1, well we know that is 2 to the 4 minus 1, which is 2 to the third, which again is just 8, so this is 3. So therefore we get a is equal to 3 over 32. Also, a fun one for the day is like these are just cool to see. So like, how do you find the area of a circle? We all know that's area equals pi r squared. So it's asking us to find the derivative of a with respect to r. And since it's respect to r, that means r is our variable. So we can just simply apply the power rule. So the derivative of a in respect to r would become 2 pi r, which is just the circumference. So the circumference is hugely related to the change of area. I also want to see, how do you find the volume of a sphere? We know the volume is 4/3 of pi r cubed. So in this question they want to know, well, what's the derivative of the volume in relations to the radius of that sphere? So again, since the radius is our input, we can go ahead and use the power rule. So the derivative of our volume in respect to the radius, so that 3 would come down and would cancel with the 4/3, so we get 4 pi r squared. So the derivative of volume is the surface area of a sphere. How sweet!